One of the most important things to find out about an object in astronomy is its distance from Earth, or its distance from the Sun. For a start, this allows us to build a sense of scale of the universe and position objects in space. For example, knowing roughly the shape of the Milky Way and how the large and small Magellanic Clouds interact with it, or perhaps the relative distances of planets around the Sun. It also allows us to estimate the size of objects. If we know the angular size an object takes up in the sky, and we know its distance from us, then we can estimate how large it is. This then leads to informing our knowledge on subjects such as how different astronomical objects are formed and what they're composed of. So the next question comes up: how do we measure distance in astronomy? There's a lot of ways because there's a vast range of distances to measure, from the scale of the universe right down to planets and things very close to Earth. But the one I'm talking about today is called stellar parallax, and it's used for, we'll say, fairly nearby objects, of order a few hundred light years. And it's a simple idea, but it's absolutely brilliant. You see, as the Earth revolves around the Sun, objects in the night sky appear to change position relative to each other. This is because they're all at different distances away, and when the Earth moves, the angle we view them at changes. To see an extreme example of this, you can set up a nearby object on a desk, with many further away at the far side of this desk. Move your head from side to side, and you'll see that the object at the front changes in its apparent position relative to those objects at the back. The trick of parallax is this. Consider the sky as a giant celestial sphere with objects incredibly far away not moving much and objects nearby moving when you view from a different angle. You can mark the angular position of an object on the sky relative to some baseline and see how it moves when you make images from different viewing angles. Then you can use trigonometry on this information. I've drawn a simple diagram of what's happening. Two images are taken from different viewing angles by moving from image A to image B along a baseline of length 2l. I observe a parallax angle of 2p, which by symmetry of angles is the angle at the top of the triangle I've drawn. From this we can use trigonometry to calculate the distance to the object. In this case, the distance from that centre point to the object is L tan p. And we can form similar equations for the distances across other parts of the triangle, because we have a roughly isosceles triangle and we know the top angle as well as the distance towards the centre. Things are going to get a lot simpler, in fact. Since parallax angles in astronomy are very small, of order arcseconds, we can actually brush past a lot of the trigonometry. Arcseconds are 1 in 3,600ths of a degree, so we can use what's called a small angle approximation to say that the distance to the object is roughly going to be L times p. But the really clever bit is still to come. Notice how I define the angle as 2p, the baseline is 2l. That's for a good reason. When astronomers have used parallax practically, they've taken advantage of the Earth's orbit at the Sun. Say the point in the middle of that diagram is the Sun, and two images are taken when the Earth is at opposing points in orbit. Then that baseline is a known and long distance. We call this the astronomical unit, which is defined as the mean distance between the Earth and the Sun. To make things even easier, we can then define a unit called the parsec. The parsec is defined as one astronomical unit subtended by 1 arcsecond. Practically what this means is that if we look at our parallax diagram, if the parallax angle here is 1 arcsecond, and the line here, half of our baseline, is 1 astronomical unit, then the distance to the object is 1 parsec. This makes calculating distances easier as long as you're using that method of the Earth revolving around the Sun. An Earth-based experiment records a parallax of 3.7 arcseconds. It's 3.7 parsecs away. Now obviously it's not quite that simple. Firstly, there's an upper limit how far away the technique works before the angular movement of the object we're observing becomes too small to see with our best telescopes. Also, this need for such high resolution demands space-based telescopes. And while I've put the baseline as 2 astronomical units, The Earth's orbit, remember, is elliptical, and the actual baseline distance depends on which 2 points you take your image at. And the most advanced parallax telescopes we have really need to account for this. However, at the very least, I hope this video has allowed you to understand the basics of the method and how it's used in astronomy. And next time I'll be going through some other interesting parts of measuring distances in astronomy. I'll be talking a bit about standard candles.